Hi, in the previous video we talked about systematic error and random error in a more mathematical perspective. In this video we'll talk about these things again, however we'll use a physics perspective that is more about how we can observe and identify these kind of errors in our experiment. In physics we always start with definition. So in terms of definition, there is one main difference between systematic and random error. For systematic error, the bias, which means the deviation from the accepted value or the truth value, will be always in the same direction. For example, if you have an electronic balance which start actually with say -10 gram, and then you measure maybe an apple, put on top of it. So every time the reading that you take actually has been underestimated by 10 gram. And if you put an orange on top of that, again it will be underestimation of 10 grams. So it's always be in the same direction. Or if you try to measure something, but then somehow because of the external factors, you always measure something that is somehow bigger, always overestimating it. Even though maybe the values could be different, then it should be accounted as the systematic error. So obviously for random error, instead, then it wouldn't be always the same direction. So it could be either overestimate or underestimation. So this is the basic difference in terms of definition. So let me give you some examples for each of them. For systematic error, like I said, one of the very common errors of systematic errors would be zero error. I have a video about zero error in IGCSE, but I'm pretty sure that you know. In case you don't know, you can see the link in my description below. So other than zero error, systematic error could also be due to some other external factors. So in the textbook, they provide you a really good examples, but I don't think they have presented perfectly. So let me try to rephrase it to you. So here, imagine there's a student did the experiment to hopefully test and verify the equation F equals to ma. So here you can see there's a card and with a string connected to a block here with mass m. So what he or she did is by changing, so increasing or decreasing the mass, hopefully that will also affect because there's a weight here, and therefore the tension that pulling the card would also be affected. So in that case, there should be a difference in terms of the acceleration. So hopefully this is the relationship that he could find out by changing the A and also changing the M of this block. So the first time when I read this, I feel kind of confused because like, why are there two lines? So what you can imagine is the student, of course, like your usual experiment, will have collected different variables. So that will including the independent variable that will be m, and also dependent variable that will be a. And so maybe it will start with say 0.1, 0.2, 0.3 in kg, right? I just look up the x-axis, and then for a will be corresponding a. So in his or her experiment, then the raw data result when it's plotted on the graph will probably be like this. Alright, something like a few dots like this. I don't think there will be any raw data here because that doesn't make sense, right? If you have put a certain mass here, you shouldn't be getting a negative acceleration because that would mean the car will go backward, right? It just doesn't make sense. Okay, the reason why the line will have a negative value here is because that student, after getting a few data, maybe more, I don't know, then he or she will start to draw a line that is the same as this one because this looks like a straight line, right? So he or she will just simply deduce, and that should be the best guess. This should be the so-called line of best fit. But then here's the problem. This doesn't make sense because first of all, we will expect a proportional line. Okay, we'll expect to see that because if you try to deduce from the formula, we will have F, which is simply the weight, which is equal to mg equals to ma. So the m, actually this m here is, oh, actually I didn't say very well. So the M here, it should refer to the big M here. So it's not changing this, it's actually changing this mg. Alright, sorry about that. But then the main idea is we are changing this M and to try to see what's the difference between this A. So eventually, when you try to look at the relationship of this, you can deduce an equation that is A over M, because the slope is A over M, and that should equal, according to the framework here, it should equal to G over the big M. Yeah, that's right. So this would be a constant, obviously, because gravitational acceleration on Earth is 9.81. This is a constant. The big M, that is the card itself, doesn't change. So it is a constant as well. So that's why you are anticipating a straight line. And there's no plus C. I mean, if you think about what you learned in mathematics, for a linear line, that will be y equal to mx plus c. But there's no plus c here. So then the y-intercept should be 0. So that's why the red line is anticipated. So that means there must be some problem with our experiment here, so that the blue line is kind of shift downward. And can you guess what the reason is? Alright, so the answer is actually friction. Very simple, isn't it? So the idea, you can take it as whenever this is moving, there must be some friction, as you have learned it in mechanics. So the value, the best part of this is from the graph, you can then estimate the amount, the exact magnitude of the friction. And that is by looking at here, right here. So that should be about 2 grams, and that should be 0.2 meter per second square. Okay, but this is not Newton, of course, but then you can actually use this to calculate the corresponding one, because you can actually calculate this by multiplying with the big M. So you can then evaluate the friction of it. More examples for systematic errors for you. So you can now see it's more involving the environment factors or the techniques or your methodology. So another example could be the way that when you take the data. So for example, when you use the measuring cylinder, the tube is supposed to be vertical, but then maybe it's tilted, so then the water level is actually slanted. So in that case, depending on which direction you're looking at, then your reading will always be either lower or always higher. Again, assuming you are always on the same side to take the data. That would be similar as if the parallax error as well. So parallax error, you should know very well, that is something to do with whether or not you are looking at the reading perpendicular to the surface. So that could apply into measuring cylinder, of course, and it could also be, for example, an analog ammeter or voltmeter as well. Also, another example could be reaction time as well, as you always are slightly slower than the actual time that you stop the timer. However, for reaction time, one way to handle it is you can always take a video and play back to the video and find out the exact time, so you don't have to react, and therefore you can take away the effect of reaction time. So we finished talking about quite many examples of systematic error, and let's talk about the random errors examples. So recall the definition again. Random error is talking about the error could either be bigger or smaller than the original. So it could be overestimate or underestimation. So example like the fluctuation we talked about in the previous video for electronic balance, or it could be any other things that usually are very sensitive, and that will produce a random error. In fact, for any kind of instrument, they will produce a random error, because if you look at this ruler, again, really every single instrument, if you look at this ruler, let's say the blue object, whatever that is a thing that you want to measure. And assuming it starts from 0, so then here you can see the ending part here, this line is in between the marking of 23, I think this is 23.2 and 0.4. So there's no way that you can judge it is 23.2 something or 23.3 something, okay, because it's between these two. So the best thing that we can get out of this particular ruler is that you can only guess which one is closer. So I think it's precisely closer to 23.2. So what I can say about this is the length of this whatever object is 23.2. However, we all know this probably it would be the best if we can guess 23.3, but we cannot say that because there's no marking in it. And therefore, in order to show how much we are confident with our measurement, then for this one, we can say that the measurement is 23.2 plus or minus 0.1. This is because we know the range of the length of this is of course in between 23.2 to 23.4, but since we believe that all of the human beings like us, alright, are intelligent enough to judge whether it is closer to 0.2 or closer to 0.4. So that means in the middle, that is 23.3, it must not exceed that line, of course. So that's why for the uncertainty, I will put that it as plus or minus 0.1. And in general, if you think about this in a general concept, then that means this will be half of the smallest division. Right? Division, that means the smallest space between the marking or the interval of your measurement tool. So here in this ruler, strangely, it is 0.2, and so divide by 2 means 0.1. So that's why it will be 0.1 here. Think about this. If you have another ruler that is like the one below, then obviously you'll be able to have a more precise, be careful, precise, not accurate, more precise measurement. So in this case, let me take a look. So I guess it is between this line and this line. And again, I still feel it's closer to the left line. And this is 32.1.2.3. So this is 32.3. This is 32.4. So then my answer should be what? Let me give you 5 seconds to think about it. The answer that I will give will be, of course, 32.3 because that's the one that is closer to the object. And plus or minus, because the smallest division is 0.1, and therefore I will write 0.05 in this case. So this could be an acceptable answer. However, well, of course with the unit, right? Let's say I guess it's cm. However, there are some people who say it would be 32.3 plus or minus 0.1. This could probably be an option, an alternative of the answer also. But this is based on the fact that you are also paying attention to the beginning of the ruler. So let's say it starts from somewhere in the ruler that is supposed to be 0. Or even you can take this one as 30, so I can take out 30 from all my answer here. That particular reading may not be exactly aligned as well, right? Because no one on earth, literally nobody, can 100% align two things together. I mean, physically, in a more macroscopic view of our world, yes, you are aligning them together. You can use your fingers or use even a tool use a metal plate to align them together, but then in fact you are not sure whether or not they are 100% aligned without any difference. So maybe there's only 0.000001 cm of difference, right? So in that case, then you can also consider that part will also have a 0.05 cm of absolute uncertainty here. And so basically what you do is add them up. So that's how you can get 0.1 cm here. So both of these answers could be acceptable. But in your IA, if you are talking about this in your IA, then you need to explain properly. However, what we say about dividing the smallest division by 2 only is applicable on analog instrument. Analog instrument means those traditional kind of instrument that is with a needle. So for example, like voltmeter, ammeter that you use in IGCSE, of course not the Vernier one. It could also be simply a timer like the traditional clock, or it could also be a ruler that we mentioned. However, for digital instrument like electronic balance or other kind of Vernier equipments that you may use in the future, those will be the digital one obviously, then the uncertainty would not need to divide by 2. So for example, if say this picture is reading 30.0 gram, then what you can say about this of the mass of these screws will be 30.0 gram plus or minus 0.1. Okay, so we just take the decimal that it can display, because when they can display, that means this is the best they can display, right? They would not, they shouldn't be hiding the number from you if they are confident to tell that. So for this electronic balance will be up to 1 decimal place. So that's why the uncertainty, unless the user manual has specified that. Otherwise, if you cannot trace that, then we'll usually take it as 0.1 gram. So you don't have to divide by 2 in this case. When I was a student, I was curious why, like I was not really well convinced why digital would not need to divide by 2, why would analog be able to divide by 2. And so I keep looking for answers. I also discuss with other teachers, not only physics but also maybe in chemistry as well. Our consensus is for digital, because we don't know what happened inside the computer, right? I mean, we ultimately are the end user. We are not the one that developed this tool, so we don't know what happened inside that is showing us the number. So maybe, for example, again this picture is 30.0, so maybe it is actually 29.2 gram. If you think about 29.2 gram, with a regular standard way of thinking in mathematics, you should round it down, right? So 29. But then who knows, maybe they always round it up, right? Maybe like it's just a thing that happened to the program or computer or the sensor itself. So our best guess should not be only half of the smallest division. So it would be safer to claim for a wider range, right? Because as a physicist, we want to be more safe. When we talk about something, if we don't know about something, then we will just say we don't know, or we can kind of enlarge the range, the possible range that is depending on the evidence that we can have. So that's why for the digital one, we will just take the last division, last decimal. That's probably be the smallest division. So I don't think this will be something that you will encounter in paper 1, 2, or 3 in the written exam, but then it will be very important for you to think about it in the internal assessment, IA. Lastly, to test your understanding, here are some examples of the source of error you may find in an experiment. So try to pause the video and locate whether or not these are systematic error or random error and the reason behind it. Pause the video now and we'll go through the discussion together.
A few moments later.
Okay, so the question is talking about measuring the diameter with the caliper. I don't know whether they are referring to micrometer or Vernier caliper. They are two different things. In case you don't remember what these two things are, I have made the videos in IGCSE. I'll put the link in the description. You can go and revisit them. So it doesn't really matter, I think, right, which one you use, but then for say part 1, it's saying that the ball is not centered between the jaws of the caliper. So you can imagine when you try to measure the ball, you have to actually clip like this, right, on two sides. But then what you do is probably you are not clipping it right, and maybe you are measuring something like upper like this, like, so you are more like measuring something like this instead, right? Wait, I mean, this is for, of course, much exaggerated, but then you can see that since the diameter is the longest distance that you can measure within, you know, a spherical object, then if you are not centered, I mean the ball is not centered, then it's always smaller. So when we say always smaller, then that must be a systematic error for number 1. Number 2, it says the jaws of the calipers are tightened too much. Alright, I assume it's always tightened too much because if you recall your experience using it, in fact, for example, the micrometer, which is the one that you turn the knob, you can actually keep turning, and then you keep going in. You can actually go far in. That is kind of like drilling the screw into an object. So that obviously is wrong because you don't want to damage the object and also affect the measurement. So this again, the bias is always towards one side, and that is underestimating the diameter. So this once again is systematic error. For number 3, it's saying that the temperature of the ball may change during the measurement. So maybe the room temperature itself during the day and night, there's a temperature change basically. So since they did not specify, like for this statement, it did not specify the temperature is going up or down, so I guess we have to assume both may happen. And according to what we understood with the size of the ball, when it gets hot, it will become slightly bigger, it will expand, right? When it's cold, it will shrink. So since we don't know whether or not the temperature go up or down, so that means it is a random error instead. Random error. Okay, for number 3. For number 4, it said the ball may not be perfectly round. So I guess how it may look like will be something like, okay, again, very exaggerated. So in this case, it's a bit different from number 1 because number 1 is assuming this is a really perfect sphere. But then for this one, this is not even a sphere, right? Then there is no clear definition of diameter in this case. What we can do is we measure multiple as much as we can, and we take the average. So whenever you take more different trials, then each trial will be different. Some of them may be larger, some of them may be smaller, and you try to calculate the average. Average, of course, it must be somewhere in between your data set. So that's why it should be random error as well, because again, maybe this one is slightly shorter, but then maybe this one is much longer. So that's why there's a difference between each measurement, and sometimes it's bigger, sometimes it's smaller. Since we talk about systematic error and random error for quite a long time, so let me give you a small summary to write this thing up. For both of the error, which are the only 2 categories of errors that we have in physics experiment, we talk about their definition and also examples. For systematic error, how we can identify it from the graph. So this is given that you have the framework, you have the theoretical formula or equations, so that you can compare your experimental data with the theoretical data. So, and if you find there's a consistent difference, like the picture that we draw, then you can then probably think of there might be some sort of systematic error in this case. For random error, we talk about how we would do for both analog and digital instrument. And lastly, I want to add one more thing, that is in most of the experiment you will be repeating different trials, hopefully to make your measurement more accurate. However, when you try to consider systematic error and random error, doing it repeatedly cannot resolve problem. Most of the time cannot resolve the problem in systematic error. For example, just now when we talk about friction, no matter how many times you do with the car, 1000 times trial, each time there's always friction, so you can't reduce that, right? It's always there. Or another example could be reaction time, right? Again, no matter how many times you do for the same measurement, there will be reaction time. So by doing it more times would not be able to reduce it. As for random error, hopefully it may reduce, because when you perform more trials, you may find out there may be 1 or 2 outliers. Actually, you are allowed to take it out. So in that case, when you only look at those cluster of data which are concentrated at a certain range, then your random error might be reduced when you do more trials. Evaluating error is always one of the most challenging part when you do an experiment, and that is one essential part in your IA in physics as well. Here in these 2 videos, I cannot cover all the scenarios and all the cases and how that is more essential to your IA. In the future, when you do more experiments and maybe your mini IA as well, you will find out more by doing your own experiment. I also make another series of YouTube video about internal assessment, and I'll put the link in the description below. If you are interested, you can go and watch them.